So let's look at the basics of an atom. Well, first of all, we want to consider what makes one atom different from another. What makes an element different from another? Of course, here you have the periodic table, and I'm sure you're familiar with that from previous years of school. And one of the things to note about the periodic table is how it's arranged. This number up here is called the atomic number. And you see, as I go across the periodic table, we're increasing the atomic number by 1. And the atomic number is the number of protons. It is what makes the atom the atom. If I change an atom's protons, I change what that element is. So elements are different because they have a different number of protons. Consider hydrogen, atomic number 1. It has 1 proton. If I could somehow add a second proton into its nucleus, it would turn into a completely different element. It would turn into helium, who has 2 protons. Its atomic number is 2. Now it turns out we can actually change one element into another, and we've been doing that for over 100 years. It doesn't occur chemically, but it's been around for a while, and it can be done. Sometimes it's relatively easy, sometimes it's relatively complicated. But that's the atomic number. Now generally we're not going to put the number down here actually, when you see it on a periodic table, it could be anywhere. Depends on the periodic table. But it's going to be the whole number, and it's usually the largest number. So here I have silver, and I see this is my atomic number. It's never going to be a decimal because I can't have decimals. I can't have part of protons, so it's always going to be a whole number. You see here I have a chemical symbol. This is an abbreviation for the element. It might be the first 2 letters, it might be something else, and this goes back to years back in alchemists and usually Latin-based words, and that's why it might be completely different than what we see here. And here's a list of the first 10 elements. And so I have their name, and here's the symbol. And you can see it always starts with a capital letter, and sometimes there's a second letter. It's always lowercase. And you see the atomic number is ascending, it goes up by 1. And you see the protons, same thing, because these 2 things are equal. Now my neutrons are going up. They're close to a 1-to-1 ratio, but not always. And we'll talk more about these later. Let's skip mass number for now, but you see that's going up as well. And the other thing we can look at is electrons, which you see I go from 1 to 10. So my number of electrons equal my number of protons. The electrons are negative, the protons are positive, and we've talked about that before. And for now, we're considering atoms are neutral. The pluses and the minuses equal each other. So this column equals this column. So let's look at this problem. I have an element of nitrogen. Here's my chemical symbol. It's in liquid form. It's being poured out here. It has an atomic number of 7. So the question is, how many protons and how many electrons in a neutral nitrogen atom? Okay, well, atomic number of 7, we said the atomic number of 7 equals the protons, so this has 7 protons. And it's neutral, meaning the pluses and the minuses are equal, so that means the electrons are also equal to 7. We can fill in this table here. We're looking for atomic number and protons and electrons. So here's K. We could look up the name for that. That's potassium. It's got an atomic number of 19. Well, these things, let's make it simple. They're all going to be equal. Atomic number is the protons, and protons equal electrons. So if this is 19, this is 19. Going backwards, I have 5 electrons for this one. That means 5 protons. That means the atomic number is 5. And I go to my periodic table and I look that up. And sure enough, it is B for boron. Sulfur, my atomic number is 16. My protons equal the atomic number, and my electrons equal the protons. My vanadium here, I looked that up to find its name. Element number 23, that's the atomic number. It's the same as protons. And my electrons equal my protons. So we talked about the atomic number, and now we need to talk about the mass number. So the question we're going to start off with is, how do we find the number of neutrons in an atom? We said that protons determine what the atom is. Well, let's think about what parts of an atom have significant mass. We've said before in section 1 that an atom has a proton, a neutron, and an electron. And we said the mass of a proton is 1. The mass of a neutron is 1. And an electron is 1 over 1,840. And again, these are in atomic mass units. They're relative values. That just allows us to compare. So this says that these are the same mass, and this is way too small. So if I said what makes up the mass in an atom, you would correctly say, well, the protons and the neutrons. The electrons are too small to worry about. So because these things make up the mass number then is defined as the protons and the neutrons. So protons have a mass of 1, neutrons have a mass of 1, electrons too small to worry about. So this is our definition for mass number. Now this is a way we can write both the mass number and the atomic number. This number on top is the mass number. The number on the bottom is the atomic number. Well, if the mass number is protons plus neutrons, that's the mass number, and the atomic number is protons, what happens if I subtract the atomic number from the mass number? Well, P minus P is 0. So if I subtract these two, I get N. I get the number of neutrons. So if I want to find the number of neutrons in an atom, all I have to do is subtract the mass number minus the atomic number. So here we're given some atoms, and we're given the atomic number and the mass number, and they ask how many protons, electrons, and neutrons. Well, keeping in what we had in the previous example, let me rewrite it. And I'm going to take the mass number and put it on top, and the atomic number and put it on the bottom. So what do I know? How many protons? Actually, I'm going to go ahead and I'm going to do that for each one. So let me do neon. Mass number of 20, atomic number of 10, sodium, mass number of 23, atomic number 11. All right, now let's figure out what we have. So they want to know how many protons. All right, well, protons is the atomic number. So my protons for beryllium is 4. For neon, 10. For sodium, 11. They want to know the electrons. Well, we said before that protons and electrons are the same because these are negative and these are positive. They have to equal each other. So our electrons, well, it's the same as protons. And then lastly, for the neutrons, we're just going to subtract vertically. 9 minus 4, 20 minus 10, and 23 minus 11. On this one, they're just asking how many neutrons. So just like we did in the previous example, this of course is my mass number. On top it's protons and neutrons, and on the bottom it's protons. So if I subtract them, I get neutrons. So for all of these, I just need to subtract. Now, just like we have different kinds of apples, and apples, they're all apples. They taste close to the same, but they're a little bit different. We have different flavors. Well, we have something similar when we're talking about atoms. So different varieties of atoms are called isotopes. Now we've said if I have an atom, and let's say we have an atomic number of 3, I can't change this. Or if I do, it's not lithium anymore. So this is lithium with 3 protons. And so if I add a proton, it becomes something else. And if I take away a proton, it becomes something else. But what I can change, what does come in different varieties, is the mass number. And the mass number is protons and neutrons. And so again, this atom, this element, has 3 protons and 3 neutrons, and I figured that out by subtracting. So with isotopes, it might come in a different mass number. I could have a different variety, and my mass number would change. So here, if I subtract, I get 4 neutrons, whereas this one, I get 3 neutrons. So these are called isotopes. These are lithium isotopes. They have the same protons because that can't change, but they have a different mass number. So isotopes are atoms that have the same number of protons, but different number of neutrons. And because they have a different number of neutrons, they have a different mass number. Now, chemically speaking, neutrons don't do a whole lot. They don't really interact much. So chemically speaking, isotopes behave pretty similar as far as how they react. And they do play a role, but we'll talk about that later. Now here we see one other way to write mass number. Here I have 2 isotopes of carbon 12 and 13. So this says diamonds are naturally occurring form of carbon. 2 stable isotopes are carbon 12 and carbon 13. They want to write the symbol using superscripts and subscripts to represent the mass number and atomic number. So we have to remember that these both, those are the mass number. So let's write it the way we've seen previously. So I'm going to take carbon, that's the symbol from the periodic table, and again this is the mass number, so it goes up here. Now it's perfectly acceptable to write it like this and leave the bottom off. But because they ask, we'll put the bottom number too. This of course is the mass number. This is the superscript because it's up in the air. The subscript, the one below, that's the atomic number. All we have to do is go to the periodic table and look it up, and we see it's 6. Alright, and then carbon-13 will do the same thing. Again, that's the mass number. Same symbol, because it's still carbon. I'll put the mass number. The atomic number, well again, I just look it up, and there it is. So these are my 2 isotopes. Now going forward past this chapter, you're more likely to see this because this is easier obviously to write than this. But for this chapter and sometimes we'll use this form. Three isotopes of chromium, chromium 50, chromium 52, and chromium 53. How many neutrons are in each isotope, given that chromium has an atomic number of 24? Now let me look up chromium on the periodic table. Its symbol. This is my mass number. I skipped one. And for each of them, the atomic number is the same, and they tell us what that is, so we don't have to look that up. And again, they're asking for neutrons, and so neutrons we can find by mass number minus atomic number. And here's a visual representation of some neon isotopes. And again, chemically they're going to behave alike because what's inside doesn't really react. So here I have neon 20, 21, and 22, where that's the mass number. The protons are the same for each because they're all neon. The electrons are the same because that matches my protons. And I subtract the mass number minus the atomic number, and that gives me the number of neutrons.